Hello, everyone. Welcome back to this online class. Today, we are going to look at how to form ordinary differential equations. In particular, we're going to look at the elimination of essential arbitrary constants from primitives. Now, we are given this example. We are asked to obtain the ODE associated with the following primitives. In part A, we have y is equals to x squared plus a exponential 2x plus b exponential negative 3x. In part B, we have y is equals to exponential 4x times a cosine of 3x plus b sine of 3x. In part C, we have y is equals to a times sine 4x plus b plus c exponential 3x. And lastly, in part D, we have ax squared plus by squared is equals to 1. So we want to see how to form ODEs from those given primitives. So let's start with part A. And before we even begin solving, what you need to take note of is that, let's write this down. Take a note that to obtain an ODE from a primitive, there are two things we're going to do. The first one is to differentiate the primitive a number of times equal to the number of essential arbitrary constants. That's the first thing you need to do. The next item, you now need to manipulate the primitive and its derivatives algebraically to eliminate the essential arbitrary constants. It should be constants. Where the essential arbitrary constants. So that's those two steps. Now there are terms that I've used here that somebody might be wondering. What do we mean by a primitive? What is it? What do we mean by an arbitrary constant? And what do we mean by essential arbitrary constants? Now, when we talk of a primitive, I'm not going to write, I will just explain. When we talk of a primitive, of course, let's first of all define an arbitrary constant. Arbitrary constant means an undefined constant in a function, a constant that you don't know its value. E.g., I could talk of this. If I have this function, y is equals to ax cubed plus bx squared plus cx squared plus d, let me not write d, let me write 3x plus 4. Let's say we have this function. Now, when we talk of arbitrary constants, there are those constants which we don't know their values. So A, B, and C are arbitrary constants. Now, what about essential arbitrary constants? Look at this equation, this function that I've given you. This can be written as ax cubed. Look at the term in x squared. You can see we can combine those two terms to get b plus c. You see, when you add two arbitrary constants, you get another arbitrary constant. So let's say where we have b plus c, let's say that is d then times x squared. Then we have 3x plus 4. Whatever I'm calling d is the sum of b and c. You're saying let d be equal to b plus c. When you add any two arbitrary constants, you get another arbitrary constant. So the refined equation, the refined function still has two arbitrary constants, a and d. And we cannot refine this equation further. We cannot simplify this refined equation further. So the constants which appear in the refined function, those arbitrary constants, now we call them essential arbitrary constants. So we cannot say that A, B, and C are essential. Why? Because the first function here can be simplified to obtain the second function, which still has two arbitrary constants, and so those are the ones that we call essential arbitrary constants. So the definition of essential arbitrary constants simply means that they are constants which appear in a function that cannot be simplified further. They are arbitrary constants which appear in a function which cannot be simplified further. Now, what about a primitive? A primitive simply means it is a function that you cannot simplify further and contains essential arbitrary constants. So in other words, it is a function which involves essential arbitrary constants. So like the function I've written in blue, that is what you're calling a primitive. Because you see, the essential arbitrary constants are a and d. So the whole of that function is called a primitive. So having explained those three terms, let's now see how to form ODEs from the given primitives. We start with part A, y is equals to x squared plus a exponential 2x plus b exponential negative 3x. So in part A, y is equals to x squared plus a exponential 2x plus b exponential negative 3x. So just follow the two steps. The first step, you need to differentiate the primitive a number of times equal to the number of essential arbitrary constants. How many arbitrary constants do we have here? A and B, there are just two. There are two essential arbitrary constants. Two essential arbitrary constants. That is A and B. A and B. So what does it mean? That we need to differentiate this equation three times. Not three times, but twice. So let's call this equation 1. Now I need to get the first derivative, call it y prime or dy dx. That is 2x plus 2a times exponential 2x minus 3b exponential negative 3x. I also need the other derivative, second derivative, that is x. No, we are now differentiating 2x, that will give us 2, not x. That should be 2 plus, this should be 4a exponential 2x plus 9b exponential negative 3. So that is the first step. We have differentiated the primitive a number of times that is equal to the number of essential arbitrary constants. In part B, or simply the second step, now we need to manipulate these three equations algebraically to get rid of the essential arbitrary constants. So we have those three equations, Roman 1, 2, and Roman 3. Now I want to start by eliminating A. Eliminate A between, let's start by eliminating A. Eliminate A. So I want to consider the first equation. The first equation is y is equals to x squared plus a times exponential 2x plus b times exponential negative 3x. So eliminate a between equations 1 and 2. The other equation is y prime is equals to 2x plus 2a exponential 2x minus 3b exponential negative 3x. How do we get rid of a from here? What do we do? You must ensure that the coefficient of the term, or simply the term involving a, is the same, so that you subtract. Look at here. The coefficient of a here is 2. So, and in the first equation, it is 1. So I'm going to multiply the first equation by 2 and the second equation by 1, so that we make the coefficient of a to be the same in each of those equations. So when you multiply, this is what you're going to get. We are going to get 2y is equals to 2x squared plus 2a exponential 2x plus 2b exponential negative 3x. And the other one, you multiply by 1, so just y prime is equals to 2x plus 2a exponential 2x minus 3b exponential negative 3x. So now we can now subtract the two equations to get rid of a. So I will now subtract. Take the second minus the first. So we'll have here y prime minus 2y, that's on the left hand side, is equals to 2x minus 2x squared. Then 2a exponential 2x minus 2a exponential 2x, that will be 0, which I don't need to write. Then I have minus 3b exponential negative 3x minus 2b exponential negative 3x. So that's minus 5b exponential negative 3x. So that's what we have. Let's call this equation star. Again, see, we also have the third equations. Again, you want to consider the first equation and the third equation. We still eliminate a between those two equations. So I'll take the first equation, equation 1, which is still y is equals to x squared plus a exponential 2x plus b exponential negative 3x. And equation 3, which is y double prime is equals to 2 plus 4a exponential 2x plus 9b exponential negative 3x. Now, what do we do again to get rid of a? You must ensure that the coefficient of a is the same. Here I can see it is 4, but here it is 1. So I have to multiply the first equation by 4 and the other equation by 1. So what are we going to get? It will give us 4y is equals to 4x squared plus 4a exponential 2x plus 4b exponential negative 3x, and the other equation is y double prime is equals to 2 plus 4a exponential 2x plus 9b exponential negative 3x. Now we can subtract the two equations. So we are going to write here that when you subtract the two equations here, what are we going to get? Let's take the second minus the first. So that will give us y double prime minus 4y is equals to 2 minus 4x squared. This and this, when you subtract, you get 0. So 9 minus 4, that is 5. So plus 5b exponential negative 3x. So that is equation star star. You see, we started with 3 equations, Roman 1 all the way up to Roman 3, and we have now eliminated one of the arbitrary constants. Now we have 2 equations, star and star star. You realize that in the 2 equations, we still have the other arbitrary constant b. So we need to eliminate them. Eliminate the constant b is just 1. So now I'll write here, eliminate b. Eliminate b between equations star and star star. So let's write star, and also let's write star star and see how to get rid of b. I'll write equation star. Equation star will write here. The other one is star star. We write it here. So let's see, equation star is y prime minus 2y is equals to 2x minus 2x squared minus 5b exponential negative 3x. And this other one is y double prime minus 4y is equals to 2 minus 4x squared plus 5b exponential negative 3x. Now, how do you get rid of b between those two equations? You simply need to add them, because I can see they have the same coefficients except the sign. One of them is negative, another one is positive. So when we add, we are going to get 0b, which is just 0. So add the two equations. So we are saying that upon adding, we are going to get y double prime minus 4y added to y prime minus 2y. We are just adding the left and right hand side is equals to 2 minus 4x squared plus 2x minus 2x squared. See what you're getting? Then plus 0b, which I don't need to write. Now let's simplify this one. This means that you can write or y double prime. What about the y prime is just 1, so plus y prime minus 6y is equals to, I can see negative 6x squared, negative 6x squared plus 2x, then plus 2. That is the ODE. You see now our equation does not have the essential arbitrary constant. So we have managed to eliminate those essential arbitrary constants. So this is the required ODE. Or you could also write this as d squared y dx squared plus dy dx minus 6y is equals to negative 6x squared plus 2x plus 2. Another way, another notation, another way of writing the same ODE. So that is the ODE that we have formed in part A. Let's see how to get the ODE in part B. Let us see how to get it. You can go back and check what was the primitive in part B. It was y is equals to exponential 4x times a cosine of 3x plus b sine of 3x. So I'll write it here again. That is part B. So you write y is equals to exponential 4x a cosine of 3x plus b sine of 3x. Now, how many constants, essential arbitrary constants, do we have in that primitive? There are just two, a and b. So we need to differentiate this equation 2 times. So this, you can call it equation 1. Now the derivatives, you write y prime. Now, even before, you see, it is easier. I don't want to use product, will be cumbersome. This equation can be written as, even before I get y prime, let me write this. This equation can as well be written as, if I multiply both sides by exponential negative 4x, I'll get this. Exponential negative 4x times y is equals to a cosine of 3x plus b sine of 3. I want to make my work easier when differentiating. That's why I got rid of the exponential function from the right-hand side, because I'll have so many terms on the right-hand side. So it is easy to differentiate the left-hand side, implicit differentiation. So now it is this that you're differentiating. In fact, let me write it this side. Even I can wrap this. We can wrap this one. So that we differentiate easily. We don't take a lot of time. So this equation, we have said it can be rewritten as exponential negative 4x times y is equals to a cosine of 3x plus b sine of 3x. This is the first equation. You see, remember, we have not differentiated. We have just rewritten that equation in another form. Now let's get y prime. Now differentiate this side, the left-hand side. I'll retain exponential negative 4x to keep it constant and differentiate y to get y prime. Now plus differentiate exponential negative 4x, that will give us negative 4 exponential negative 4x. Now y is a constant, is equals to, remember we used implicit differentiation on the left-hand side. On the right-hand side, when you differentiate, you get negative 3a sine 3x plus 3b cos 3x. That's what you get. Or this simply implies that y prime minus 4y times exponential negative 4x is equals to negative 3a sine 3x plus 3b cosine of 3x. That is the second equation. Remember, we need to differentiate twice. So this is the first derivative. Let's get the second derivative. Again, I'm going to use implicit differentiation on the left-hand side. So when you differentiate this equation, what do we get? We are going to get, let me differentiate this while keeping this constant. So we'll have, you can delete those ticks. When you differentiate that, you get y double prime minus 4y prime, keeping exponential negative 4x constant. Then now plus, I want now to differentiate exponential negative 4x while keeping the whole of this constant. So that will be minus 4 exponential negative 4x, keeping y prime minus 4y constant, is equals to the right-hand side. When you differentiate the right-hand side, you get negative 9a. That should give us cosine of 3x minus 9b sine of 3x. And so this implies that if I simplify left and right hand sides, it is the same as y double prime minus 4y prime. Then I can see another 4y prime minus 4y prime again plus 16y. Then the exponential negative 4x is common, is equals to, I can see negative 9 is common. So here we'll have a cosine of 3x plus b sine of 3x. And I could simplify the left-hand side further. Let me combine those y prime, negative 4y prime, another negative 4y prime. You could write here or y double prime minus 8y prime plus 16y. The whole of these times exponential negative 4x is equals to negative 9 a cosine of 3x plus b sine of 3x. So this is the third equation. So we have managed to obtain the derivatives of the given primitive. Now we need to manipulate these derivatives and even the primitive. Let's see whether we can get rid of a and b. Look at equation 1. From equation 1, we are told that a cos 3x plus b sine 3x is the same as exponential negative 4x times y. And look at again this, we still have a cos 3x plus b sine 3x. So we are going to substitute equation 1 into equation 3 so that you can get rid of a and b. So substitute. Substitute equation Roman 1 into the third equation. So what do we get? We are going to get the third equation is y double prime minus 8y prime plus 16y. The whole of these times exponential negative 4x is equals to negative 9 times exponential negative 4x times y. I have replaced this. It is this one. And we are told it's supposed to be equal to exponential negative 4x times y. So when you divide by exponential negative 4x, it will cancel out. This will disappear with this. So you can say or y double prime minus 8y prime plus 16y is equals to negative 9y. So the next thing is to take negative 9 to the left-hand side. When you cross over, it becomes positive 9. So 16 plus 9, that will be 25. So you can just say that therefore, we'll have y double prime minus 8y prime plus 25y is equals to 0. Look at that equation. That is an ODE. You can see we have managed to eliminate the essential arbitrary constants. So this is the required ODE. You can bracket it. This is the required ODE. As long as you have a differential equation without those constants, then that means that's the equation that you need. So this is the ODE. Let me not call it equation star. It is the required ODE. You realize that we have not used equation Roman 2. Because we have said as long as you can find whichever, you just manipulate them algebraically. You don't have to use all those equations to obtain the ODE. But we have used Roman 2 to get Roman 3. That's very important. In part C, let me write the question down. We have y is equals to a sine 4x plus b plus c exponential 3x. So how many constants, how many essential arbitrary constants do we have here? So there are 3, A, B, and C. 3 essential arbitrary constants. So you differentiate 3 times. Differentiate 3 times. So this will be our first equation. Now y prime is equals to 4a. When you differentiate sign, you get cosine of 4x plus b, then plus the derivative of c exponential 3x, that will be 3c exponential 3x. The other one, y double prime, is equals to negative 16a. That should be now sine of 4x plus b, then plus 9c exponential 3x. Then lastly, we have y third prime to be equal to negative 16 by 4, that is 64a cosine of 4x plus b plus 27c exponential 3x. So this is equation 2. This is equation 3. And this is equation 4. Now, how do we manipulate them? I want to get rid of A, B, and C. Let's start by getting rid of A and B. You see, A and B are combined in the sine or cosine functions. So look at equation Roman 1. From here, we know A sine 3x, so A sine of 4x plus B, sorry. Now, you can also find A sine of 4x plus B here. So I'm going to substitute equation 1 into equation Roman 3, where we have A sine 4x plus B is the same as, I can make this the subject, this one. It is the same as y minus c exponential 3x. So we can just say substitute. Substitute 1 into Roman 3. So how will the equation Roman 3 look like? It will be y double prime is equals to negative 16. Instead of A sine 4x plus B, I'll write in bracket here, I'll write y minus c exponential 3x. Then there's plus 9c exponential 3x. If I simplify, you can write or y double prime is equals to negative 16y plus 16c exponential 3x plus 9c exponential 3x. And so what will it give us? This will give us y double prime plus 16y is equals to 25c exponential 3x. So let's call this equation star. Again, go back to our primitive and its derivatives. Look at here, where we have a cosine of 4x plus b. We can also find it in equation Roman 4. So then make this the subject. What is it equal to? It is y double prime minus 3c exponential 3x, then divide by 4. Just from this, you can write a, where we have a cosine of 3x, not 3x, that should be 4x plus b. This should be 4x plus b. What should it give us? It should give us y prime minus 3c exponential 3x, and this you divide by 4. So let's substitute it here in equation Roman 4. So you can write substitute equation 2 into equation Roman 4. What are we going to get? So let's write equation Roman 4. So it will be y third prime is equals to negative 64. Instead of a cos 4x plus b, I'll write y prime minus 3c exponential 3x, and the whole of this you divide by 4. That's what we have there. Then I can see this plus 27c exponential 3x. Now you can simplify this further. 64 divided by 4. 4 will go into 64 how many times? That is 16 times. So this can be written as y third prime is equals to negative 16 y prime plus 48 c exponential 3x plus 27 c exponential 3x. And then you can combine the terms involving c. You can write therefore, simply this implies that y third prime then plus 16y prime when you combine 48 and 27, that will give us 75 c exponential 3x. So I'll call this other one equation star star. Now we have two equations. We started with 4 equations. Now we have reduced them to 2 equations. The one we call star and the other one is star star. If you look at those 2 equations, you realize that they still contain the arbitrary constant c. We need to get rid of c. So you now write eliminate c. Eliminate c between equation star and star star. How do we get rid of C? Look at the coefficient of C in the first equation, that is star, that is 25. What about in equation star star? It is 75. I want to make those numbers the same, so I'll have to multiply equation star by 3. Let me write those equations before I even multiply. So we'll write equation star and star star. Our equation star is y double prime plus 16y is equals to 25 c exponential 3x. The other one is y third prime plus 16 y prime is equals to 75 c exponential 3x. So what I'll do here is to multiply this equation by 3 and this you multiply by 1. Now what will we get upon multiplication? We are going to get 3y double prime, 16 by 3, that is 48. 48y is equals to 75 c exponential 3x. And the other one multiplied by 1 is just the same equation, y third prime plus 16 y prime is equals to 75c exponential 3x. So now I can subtract the two, subtract these two to get rid of c. When you subtract, what do we get? We are going to get y third prime plus 16y prime minus 3y double prime minus 48y is equals to 0. So this is the required ODE. Let me just rearrange it. You can just say, therefore, y third prime minus 3y double prime plus 16y prime minus 48y is equals to 0. So this is the ODE. You can see now this equation lacks the essential arbitrary constants A, B, and C. So this one here is the ODE. Lastly, let's look at part D. How do we obtain an ODE from the primitive in part D? We are given ax squared plus by squared is equals to 1. That's what we have. There are two essential arbitrary constants in this primitive, that is a and b. So we need to differentiate this equation 2 times. Let's see the first derivative. Use implicit differentiation here. So this is the first equation. Differentiate using implicit differentiation. So on the left, we'll have 2a x. We are differentiating with respect to x, both sides, plus 2b y, but then there's times y prime. Remember, implicit differentiation, you want dy dx. When you differentiate 1, you get 0 because 1 is a constant. And so from this equation, you realize that 2, of course, the 2 will cancel, or simply write 2ax is equals to negative 2 by times y prime. Or this you can also write as, let me write along another line. Or if I make a over b the subject, remember the 2 will cancel, so that a over b is equals to negative y prime over x. That's what we have. So this is equation 2. Again, let's differentiate this further. We need the second derivative. When you differentiate that, you're going to get 2a. Remember, differentiating with respect to x, 2a plus 2b is a constant. Now, use product rule to differentiate y and y times y prime, because those are functions of x. So you keep y constant, differentiate y prime, that will give us y double prime, plus now differentiate y, you get y prime, keeping the other y prime constant, is equals to 0 on the right hand side. And this can also be written as, you see, 2 and 2 will cancel. Now I want a over b. So from here, you can get a over b, make that the subject, is equals to, that now will be negative of y double prime plus y prime times another y prime. So this will be our equation Roman 3. Remember, I want to get rid of a and b. Look at equations 2 and 3. This one and this, I can equate them because the left-hand side is a over b. So I can equate the right-hand sides of those two equations. So you write equate the right-hand sides, right-hand sides of Roman 2 and Roman 3. So what do we get? Let's start with Roman 2. So that's negative y prime over x is equals to negative y double prime plus y prime times another y prime. And you see the negative will cancel. So this negative will cancel with this. I can multiply through by x so that I get, or y prime on the left is equals to x times y double prime plus y prime squared, y prime, and this is supposed to be squared. If I rearrange, you write or xy times y double prime plus y prime squared minus y prime should be able to give us 0. And that is the required ODE. It lacks the essential arbitrary constants. I've left something, there's an x here. You see I was opening the bracket on the right hand side. So here I expect plus x. It is from here. When you open this bracket, you get y double prime plus x y prime squared. Then now you take this to the right hand side, it becomes a minus. So that will be our ODE. So this is how to form ODEs from primitives. All you need to do is to follow the two steps that I have highlighted up there, that you need to differentiate the primitive a number of times that is equals to the number of essential arbitrary constants, and then you manipulate the primitive and its derivatives algebraically to get rid of the essential arbitrary constants. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in formation of ordinary differential equations. Bye-bye.